Hello again, my name is Tom Irvine, and I'm the instructor for this series of shock and vibration webinars. And I again thank Dr. Curtis Larson and the NASA Engineering and Safety Center, NESC, for making this series of webinars possible. Today we're going to start fatigue analysis, and we will actually spend probably maybe the next 5 or 6 webinars on fatigue. And today we're just going to start off with something fairly simple, and it's going to be circuit board fatigue response to random vibration. And this comes about to us through the fine work of Dave S. Steinberg. And he wrote an excellent book, and it's called Vibration Analysis for Electronic Equipment. And this is the #1 reference for this field. And even if you only deal with plates and shells and pure mechanical structures, this is still an excellent book, an excellent reference book. He doesn't spend a whole lot of time on theory, rather he has a lot of practical calculation methods for doing this type of analysis, both for electronics and for just plain mechanical structure. Our concern here is going to be avionics boxes. Now on the left we have what you might call an interstage or a frustum shell or some other name. It's a portion of a rocket vehicle, or as we like to say, a launch vehicle. And in order to make that launch vehicle fly, there needs to be telemetry transmitters, C-band transponders, flight computers, battery boxes, pyro driver units, flight termination logic units, and a whole array of additional avionics components. And the concern is that during powered flight, those avionics are going to need to withstand shock and vibration environments. So obviously they must be designed and tested accordingly. So on the right image there's an avionics box of some sort, and it's mounted to a cube fixture, which is in turn mounted to a shaker table, and the avionics box is undergoing vibration testing and possibly also shock testing as well. So what we would like to do in an ideal world is have the opportunity to take each and every one of these avionics before they are tested and do some analysis to determine the circuit board natural frequencies, to determine whether or not fatigue failures are going to be an issue. And wouldn't that be nice if we had that opportunity? But usually, because of cost and schedule concerns, the only time we really have an opportunity to do this analysis is after a given avionics box has had a failure during vibration testing. So that's just kind of the way it is. So I guess the techniques I'm going to show you are, in the real world, only used for failure analysis rather than as any type of predictive methodology. So here's a circuit board, and our concern, and this comes from Steinberg's work, is that those lead wires and solder joints are going to fail, that those are the weak links. And the circuit boards themselves are going to be undergoing bending vibration. Now if you want to get into all the theory, there's also torsional vibration modes and membrane modes and longitudinal modes and all sorts of other vibration modes. And we can even start talking about wave behavior. But the driver is going to be the bending modes, and more particularly the fundamental bending mode of the circuit board. That is what's going to induce that stress, most of the stress, into those lead wires and also the solder joints. So what Steinberg has come up with, and here I'm just going to mention that Steinberg had access to some body of data, and he never tells us what that data is. We sometimes refer to it as Steinberg's secret stash of data. But he did give the empirical formulas that he came up with based on the data that he was privy to. And I guess we'll say that was just all proprietary data. But anyways, he came up with a fatigue limit. And this fatigue limit is given in terms of the maximum allowable 3 sigma relative displacement of the circuit board as measured at the center of the circuit board for the case of 20 million stress reversal cycles at the circuit board's natural frequency. And we're assuming here that the vibration environment is broadband random vibration, stationary steady state with a Gaussian distribution. Now at this point some of you are probably scratching your head and say, well, wait a minute, my component only has to survive 1,000,000 stress reversal cycles, or my component actually has to have an extensive long life and it has to undergo 100 million stress reversal cycles. And others of you are thinking, well, my circuit board is going to be subjected to non-stationary vibration, so what can I do? And the answer really to all those questions are going to be covered in the next webinar. It is possible to take what Steinberg has done and just extrapolate it for the case of either fewer or greater than 20 million stress reversal cycles, and we can even use it for non-stationary vibration. But let's just call that next week's topic. And today we're just really starting out and covering just only the very basic. So our concern here is the flexing or bending of these circuit boards, and that's represented by the relative displacement Z. Then there's a number of geometric and other parameters. There's H, that's the thickness of the board. There's the length of the component L. There's B, which is the length of the circuit board parallel to the component. And then there's a few others I'll show you shortly. So again, the concern is the circuit board is going to bend, and that's going to induce stress in the solder joints and in the lead wires. So that's what we're concerned about. I guess you could also say, well, what about this circuit board material itself cracking, or what about things going on actually inside that black box component or piece part? Well, those also can be concerns, but again, the weak link tends to be the solder joints and these fine lead wires. So let's see. So Steinberg, he based his theory on a circuit board that is simply supported about its perimeter, and you're going to say, hey, wait a minute, I've got a circuit board with other boundary conditions. And don't worry, we can kind of, with just a little bit of hand waving, take Steinberg's methodologies and apply it to other boundary conditions as well. So this covered the middle bullet there. So again, this is kind of going to be a repeat here. Let Z be the single amplitude displacement, and it's the relative displacement, at the center of the board that will give a fatigue life of about 20 million stress reversals in a random vibration environment based on the 3 sigma circuit board relative displacement. So this Z is going to be a not to exceed threshold, and it's going to be based on an empirical formula. And here's Steinberg's empirical fatigue formula, which is widely used throughout the industry. So again, Z is the 3 sigma relative displacement at the center of the circuit board, and that is equal to, and in the numerator we have 0.00022. That's definitely an empirical constant. And by the way, this is all going to be based on inches for the various length parameters. So B is the length of the circuit board edge parallel to the component in inches. And square root of L is the length of the circuit board in inches. R is a position factor. We'll talk about that momentarily. H is the board thickness. And C is an empirical constant. It can be as low as 0.75 or as high as 2.25. So another way to think about this formula is that sometimes these parameters are just going to become a little fuzzy, because this is really based on kind of a simply supported rectangular circuit board. And I was actually on a project once that had crescent-shaped circuit boards for a missile assembly. And sometimes it's going to be a little bit ambiguous as to what the this piece part constant is, or even what the what this R position factor is. So what my advice to you is, if there's any question, please use the upper limit estimates for these 4 parameters here, and conversely use the lower estimate for B here, and that will give you a conservatively low 3 sigma limit, which is again the not to exceed limit. But let's go ahead and just review some of these parameters in a little more detail here. So this position factor R. Now, what I want to tell you is that if you're not sure what R should be, set it equal to 1 because that's most conservative. But this is the position factor where the piece part is mounted relative to the center of the circuit board. So if it is smack dab in the middle of that circuit board, it's equal to 1. If it's at the half point X and the core point Y, 0.707. When the component is at the core point X and the core point Y, 0.5. Now again, you may have some oddball shaped circuit board that's non-rectangular, and it may be ambiguous. You might have a board with intermediate standoffs. So just any ambiguity, set R is equal to 1. That's most conservative. Okay, now these component constant here is, now I'm not going to come off and tell you that I'm some kind of electronic packaging specialist, because I'm not, but I do know a little bit, and I'll share that with you, and this comes from Steinberg. And I'm going to show you a series of piece parts, and some of you are going to laugh and say, well, those piece parts are obsolete. We don't even use them anymore. They're so obsolete you cannot even find them on eBay. but here we go. Let's just do the best we can. So if we have an axial leaded through-hole or surface-mounted component, including resistors, capacitors, diodes, C is equal to 0.75. And here I show just an axial leaded resistor there, and I probably should also add an image for a surface mount component, because those are all in the same grouping there. The standard dual inline package, C is equal to 1.0. Some part, I'm sure it's obsolete by now. Dual inline package with side brazed lead wires, C is equal to 1.26. Through-hole pin grid array, PGA, with many wires extending from the bottom surface of the PGA, C is equal to 1.0. Surface-mounted leadless ceramic chip carrier, LCCC, 2.25. Surface-mounted leaded ceramic chip carriers with thermal compression bonded J wires or gull-wing wires, C is equal to 1.26. Surface-mounted ball grid array, BGA, C is equal to 1.75. Now, these are very popular these days, and many of the students that I've worked with have been very concerned about these types of components. There's a device, they used to be called pacemakers, but now they have a more sophisticated name. But anyways, I was working with some engineers from that from a particular medical electronic component that made those types of devices that used BGAs. So as you're looking at these piece parts, you're probably going to laugh because you know, the way these companies go, they merge, they change names, they get bought out, and piece parts change, new ones come along, but just sort of humor me with a little bit, and I probably need to go and do some research, literature search, and look at conference papers on what the latest types of piece parts are. Just a couple others. C is equal to 0.75. That's fine pitch surface-mounted axial leads around the perimeter of a component with four corners bonded to the circuit board to prevent bouncing. Or C is equal to 1.26. Any computer with two parallel rows of wires extending from the bottom surface, hybrid, PGA, very large scale integrated, VLSI, application specific integrated circuit, ASIC, very high scale integrated circuit, VHSIC, and multi-chip module, MCM. Now, if you have a piece part that it just isn't in this listing here, or it's just something, new, some brand new, totally different than anything that's been done before, just be conservative and set C is equal to 2.25. And hopefully, even with that conservative assumption, you'll show that you have plenty of margin so that there's no need to worry or fret any further. Okay, let's see what else we have here. So we actually are going to have a two-step process here. And the first step is to calculate the allowable limit for the piece part in question. then we're going to calculate that. That's from the Steinberg formula, the not to exceed limit. Then the second step is to calculate the circuit board's actual relative displacement. Now, circuit boards, they actually behave in many cases as multi-degree of freedom systems. So we might need to do a finite element analysis to calculate the board's relative displacement under a random vibration environment. But to some extent, many circuit boards tend to be either single degree of freedom systems, or even if they are responding as multi-degree of freedom systems, most of the stress tends to be tied up in the fundamental mode. So we can, for the most part, get away with some simplifying assumptions. But having said that, yes, there are exceptions. So if there's any doubt about what I just said, please do a finite element modeling. If you can do some type of a modal test on your circuit board, that's great too. That data is useful. But we're just going to go ahead and assume a simple single degree of freedom system. And we're also going to talk about a reintroduced Miles equation, which is just a quick hand calculation method for determining the response of a single degree of freedom system to a PSD base input. Now, some of you that are particularly astute are saying, hey, wait a minute, didn't you a number of webinars ago teach us a better than Miles method that sometimes you refer to as the general method? And the answer is yes, and I think as a bonus I'll include that method here at the end of this presentation. But just to be consistent with Miles' equation, or Steinberg I should say, we're going to use Miles' equation. Okay, so when I say Miles' equation, there are different forms of Miles' equation. Here, this term here, Q, that's the amplification factor. You might come across a Miles' equation that instead had the viscous damping ratio. There are Miles' equations for applied force, and there's Miles' equations for base excitation. This particular one is for base excitation, and it's for the 3 sigma relative displacement response. And we're assuming, well, let me just go through these terms here. Well, okay, let me tell you what the assumption is here. Is that after we get through this equation, this factor is chosen so that the unit will be inches. Probably ought to add that to the slide. So anyways, we have 1 over the natural frequency raised to the 1.5th power, then square root pi over 2, amplification factor Q. Now A is the input power spectral density amplitude, G squared per hertz, assuming a constant input level. And really to make Miles' equation work, the PSD should be flat within plus or minus 1 octave of the natural frequency. In fact, while we're here and I still have this in my mind, I'm going to go ahead and put that this is inches here, just to make that clear. So if you're in Europe and you're doing the metric system, just you can do your own conversion, unit conversion. Okay, so let's go back to full screen. Okay, so we're going to take an example. So here's this ridiculously obsolete dual inline package here, and we're going to say that it's since it's a dual inline package, C is equal to 1. That's the piece part coefficient. It's mounted at the center of the board, so we'll say R is equal to 1.0. The circuit board thickness is 1/10 of an inch. The length of the dual inline package L is equal to 0.75 inches. The length of the circuit board edge parallel to the component is B is equal to 4.0 inches. So we're going to calculate the relative displacement limit in inches using this Steinberg formula. And by the way, if you because of the latest and greatest technology, you have some piece part that maybe, who knows, it's a crescent shape or some really odd shape, then just take the largest characteristic dimension of that component, that piece part, and just plug it in here. Now, this is easy enough as a hand calculation. That's why people like it. But in order to help you, so you don't need to fret over how many zeros to put in there, I've got, as you might imagine, a MATLAB script for doing this formula. just to make it a little easier. So let's go to vibration data, and let's see what version we're up to this week. So 6.5, and here we have under miscellaneous Steinberg's circuit board fatigue. So let's click on that, and here's the Steinberg formula. You've seen that before. So this script calculates Steinberg relative displacement limit for a circuit board in inches, and this is the inch 3 sigma for 20 million cycles. And I'm just going to type in those parameters which I've memorized from that slide. So first the 3 geometrical parameters. So let's see, was it 3/4 of an inch, I believe. better double check myself there. It's yep, 0.75 inches. Okay. And we can either just enter in where our C value is, or just as a little library here, we can go down and say, yeah, we've got a standard dual inline package. So now we're going to calculate. So down in this box we have the 3 sigma Z, the not to exceed limit for 20 million cycles. And if we round off just a tad, that's 10 thousandths of an inch. So that's for the center of the circuit board. It can have a relative displacement up to 10 thousandths of an inch. And that's to allow that piece part to withstand 20 million stress reversal cycles reference to the natural frequency. So at this point we're only half done, because now we have to consider, well, what is our predicted C3 sigma? So let's go to the other part of the exercise here. Okay, here's just a screenshot of what we just did, just for your reference. Okay, so let's say a circuit board, hypothetically, has a natural frequency of 200 Hertz and an amplification factor of Q is equal to 10, and that's equivalent to saying 5% viscous damping. And it will be exposed to a base input of A is equal to 0.04 G squared per Hertz. So that is the base input at the natural frequency, and we are pretty much assuming that the PSD is flat within plus and minus 1 octave relative to 200 Hertz. So what is the board's predicted 3 sigma displacement? So as you might recall, I think this is a review exercise, we can do a Miles type of equation using our GUI package here. So let's go to single degree of freedom response, sine, random, and Miles equation. Let's begin the miscellaneous analysis, and we can choose Miles equation. So here we are with our Miles equation, and 200 Hertz is our natural frequency. Q is equal to 10. Our PSD input is at the natural frequency is 0.04 G squared per Hertz. Let's go ahead and do the calculation, and we're going to get 6 different response metrics there. And today we're concerned about this here. Relative displacement results, 3 sigma. And what we see is that for this case, our expected 3 sigma relative displacement is 8 thousandths of an inch. So, as you recall, let me see if I can get these 2 dialogues up here. Here is what we expect to happen, 8 thousandths of an inch relative displacement at the center of the circuit board, 3 sigma relative displacement. Here is our not to exceed limit, 10 thousandths of an inch. So this means we are good to go for 20 million cycles. So that's a good piece of news for us. Now let's assume that all things are equal. All other things being equal, what would happen if we stiffen up the board to make it 400 Hertz natural frequency? And we're essentially assuming again a flat PSD. So all other things being equal, that 3 sigma relative displacement at the center of the circuit board drops to about 3 thousandths of an inch. So that means we're in even better shape than before. So what this is telling us is that in terms of Steinberg fatigue methodology, it is best to have a stiff board with a higher natural frequency, assuming a flat input PSD. Well, what if, on the other hand, we had a more compliant circuit board and it was only 100 hertz natural frequency? All other things being equal, now the 3 sigma relative displacement it's about 23 thousandths of an inch, and that is at least 6 dB higher than our threshold here. So this means failure occurs prior to 20 million cycles. So again, for a flat, let's just assume that's a flat white noise PSD, and damping is independent of natural frequency. It is best to have a stiffer board with a higher natural frequency to cut down the relative displacement so that there is less board bending, so that there is less stress on the solder joints and lead wires. But there's always more to the story than that. Relative displacement, as important as it is only one metric. We're also concerned about the acceleration response. And we might, if we're following what Dr. Gaberson publicized for years, relative velocity or pseudo-velocity could also be an important parameter because it's proportional to stress without any without consideration of the natural frequency. So we're going to need to think about that just a little bit more. Now, for my design rule of thumb, here's what I'd recommend. My ideal avionics box has a very stiff circuit board inside, but on the outside of the box housing, that same component is mounted via soft isolators or bushings or grommets, whatever you want to call them. That will take the natural frequency of the box itself down to a very low frequency, so it will attenuate the shock and vibration that propagates into the board. But once that attenuated shock and vibration does propagate into the board, that board is so stiff that its relative displacement of the board itself relative to that incoming excitation will be negligibly low. Now, having said that, there are reasons why sometimes we cannot mount the outside housing via isolator springs. Maybe the box needs to be hard mounted. Maybe it's a transponder that puts out a lot of heat energy and it needs to be hard mounted to a thermal ground plane, and some intermediate solutions like a thermal grounding strap would not be good enough, so it has to be hard mounted. We cannot use isolators. So in that case, with some caution, I would still encourage a stiffer board with a higher natural frequency to reduce the relative displacement. But things are not always so simple. Let's just do another kind of consideration calculation here. So let's go back to the case where we were at 200 hertz. All other things being equal. We've got 8 thousandths of an inch 3 sigma relative displacement. That is less than our threshold of 10 thousandths of an inch, which means we're good to go for 20 million cycles. Well, how long is 20 million cycles? How can we convert that to a duration? Because our program manager just wants to know how long, how many hours that part can endure. Now, just as another little caveat of caution here, we're assuming that base input PSD is stationary and it's the one and only environment that component is going to be subjected to, which generally speaking is not going to be true, but let's just go with that. Let's just say that our 0.04 G squared per hertz input level is conservative relative to any subsequent environments. Okay, so let's say we've got 20 million cycles, so I'm going to type in 20e to the plus 0.6 in MATLAB here, and I'm going to say, okay, what is going to be the duration? Well, we've got a natural frequency of 200 cycles per second, 200 hertz. So we can take cycles divided by cycles per second, and that will give us the duration in seconds. And what you have to remember here is that the response is not going to be pure sinusoidal. It's going to be narrowband random. But it's going to be narrowband random centered around 200 hertz. So we can, just with a little bit of hand waving, assume that we can calculate the effective duration based on oscillations at 200 hertz. Now, the number of seconds is going to be so huge, let's just divide that by 3600 to convert to hours. So the 20 million cycles is good for, or equivalent to 27, let's just round that up and say 28 hours. So that means we're good to go for 28 hours at a constant input level of 0.04 G squared per hertz. So that's just another thing that we can do with this calculation, how that calculation works out. And for those of you who are saying, well, wait a minute, I've got a multi-degree of freedom system, I have two modes participating or whatever, don't worry, we'll cover that next week. All of these things can be extended to other environments, non-stationary, to other numbers of cycles. Yeah, this is just the basis. This is just the simplified basis we're starting out with. I just want to cover the basics first. Now, today we've used Miles' equation, and that's to just kind of harmonize ourselves with what Steinberg has in his text. But I want to show you the better method here, the better than Miles' method. So let's have a PSD input, and we're going to do a single degree of freedom response to the base input. This is going to be, we've done this before, it's a review exercise. And we're going to say that our input is the NavMat base input. We've worked with that this NavMat spec before several different times. And this NavMat spec, it actually has a plateau that is 0.04 G squared per hertz. So that can tie in nicely with the exercise we've already been working on today. So since it's a spec with 4 breakpoints, we do need to interpolate it. We'll go with 200 hertz natural frequency, Q is equal to 10. Let's plot from 10 to 2000 hertz. Now we're going to input duration, and this is actually not going to affect the parameter that we're interested in. This would only be for the Rayleigh distribution type calculation, but I'll just type in 60 seconds. So when we calculate it, well, okay, we've got graphs coming up, we've got just a table of results here, a list box, I should say, whatever you want to call it. Okay, so our single degree of freedom, relative displacement response, for the 3 sigma value, this is the one that ties in with Steinberg. It is about 1/8,000th of an inch. And you might say to yourself, hey, wait a minute, that's just the same as what we got from Miles' equation. So isn't Miles' equation good enough? Well, the answer is kind of both yes and no. If we go to figure 1, this is our NavMat base input. By the way, this is a power spectral density plot, G squared per hertz versus frequency in hertz. And this plateau here, it does have a level of 0.04 G squared per hertz. But what if our natural frequency fell on this ramp here or this downward slope here? In that case, Miles' equation would start to give us some error. How much error? Well, you can do your own numerical experiments. But anyways, this is the base input PSD, and this blue curve here is our response PSD. And most of the energy is concentrated about 200 hertz, which is the natural frequency. And we would call this a narrowband random response. We've talked about these before. So far so good here. There's also a power transmissibility plot, G square out over G square in versus frequency in hertz. We've talked about these before. We get unity gain at the lower natural frequencies. Then as the frequency approaches the natural frequency, we get the resonant dynamic amplification. So most of the energy is going to be centered around 200 hertz. And then at higher frequencies, the energy is attenuated. So our spring mass system is acting, we might call it a low-pass filter because it's filtering out this high-frequency energy, or we might call it a band-pass filter because it's amplifying the energy in this particular band. So it's kind of a cross between a band-pass filter and a low-pass filter, roughly. Let's just do one other thing. So this is just kind of review exercises here. Let's do another review exercise. So let's go to vibration response spectrum under PSD. We've done this before. So this script calculates the vibration response spectrum, VRS, of a single degree of freedom system subjected to a base input power spectral density. We'll talk about fatigue damage spectrum in an upcoming webinar. The input array must have two columns, frequency in hertz, and acceleration in units square per hertz. For our case, that'll be g. So we're going to use our NavMat spec as our base input, and that does have the plateau at 0.04 g squared per hertz. We've got English units, Q is equal to 10. Duration does not affect our calculation. I'll just put in 60 seconds though. Let's plot from 10 to 2000 hertz. Calculate the VRS. Whole bunch of plots come up. Okay, this is the one we want to focus on first. It's relative displacement vibration response spectrum. Q value duly noted. We've got relative displacement in inches versus natural frequency in hertz. Red curve, 1 sigma. Green curve is the curve of interest for the Steinberg calculation. It's the 3 sigma. Blue curve is the peak curve based on Rayleigh distribution, and that does depend on duration, but the blue curve does not tie into Steinberg's, at least not yet. Maybe next week it will. So the green curve is our curve of interest, our response metric of interest. And let's get our little cursor going here. 200 hertz. Again, you can see that the relative displacement for 3 sigma at the center of the board is 8 thousandths of an inch at 200 hertz. And we recall our limit is 10 thousandths of an inch. So that would be a horizontal line drawn across here. So at 200 hertz, we're good to go for 20 million stress reversal cycles. And we're even in better shape yet if we have a higher natural frequency. So more longevity with a higher natural frequency. On the other hand, if we go downward in natural frequency, it looks like we cross the threshold at about 175 hertz. So at 175 hertz, the failure would occur close to 20 million stress reversal cycles. But then if we take our natural frequency even lower, you can see that we're just in worse shape yet, and failure occurs before 20 million stress reversal cycles. So if our sole concern is relative displacement, we want that circuit board natural frequency to be as high as possible, given Q is equal to 10 and given the NavMat base input. But there's always more to the story, so let's go ahead and start. We like to worry as engineers. We're obsessed about things. So here's the acceleration vibration response spectrum. Again, Q is equal to 10. We've got acceleration G versus natural frequency in hertz. And our metric of interest is the green curve. That's the 3 sigma acceleration. And this is showing kind of an opposite trends of sorts, in that the higher up we go in natural frequency, the higher our acceleration response is going to be. And it could be that there's a potential piece-part failure mode that correlates best with more closely with acceleration than with relative displacement. Who knows? You might have a very sensitive crystal oscillator where the internal crystal would shatter if the G level is too high, as one example. There is a bit of a plateau here, so as the natural frequency goes above about say 400 hertz, there's kind of a diminishing returns effects. But anyways, if we wanted to minimize acceleration, if that was our concern, we want the natural frequency to be as low as possible. So my solution is, okay, let's make the board itself as stiff as possible, and let's take that housing and mount it via compliant soft spring type grommets, bushings, or isolators. And that's really the ideal way of attenuating shock and vibration in order to ensure reliability and robust design and performance and longevity and all those good things. Okay, so I think that wraps it up for today. Please repeat these exercises for your own homework. And next week we're going to be taking Steinberg's theory to the next level. So everyone, enjoy the rest of your day, and we'll catch up with you next week. So thank you, and goodbye.